cell, and instead of characterizing every point by its x, y, and z distances from an axis, let's characterize it by how rapidly or slowly curvature is changing at that point. That is the rate of change of curvature at every point. This turns this space into a field of rapidities and slownesses. It's not an XYZ, a set of XYZ addresses anymore. It's a different conception of space. When Gauss invented differential geometry, since it's the differential calculus that he's using, he called it differential geometry. Let me, by the way, first, let me show you a plane like this, a folded surface, but viewed from the side, say, like that, so that you can see a little bit more what I mean by the speed at which curvature changes. In this flat part, curvature is not changing, so the speed is 0, begins accelerating, it changes direction, picks up speed again, slows down a little bit, picks up speed again, and then gets to 0 again. In other words, at every point, there's a rapidity or slowness with which curvature is changing at that point. This doesn't connect directly to what we were talking about. It is a step in that direction. Because before getting to topology, we had to get rid of the Cartesian coordinates. We had to be able to study spaces by themselves. Gauss solved the two-dimensional problem. Riemann, his disciple, was supposed to solve the three-dimensional problem. You know, your master solved 2D, you go for 3D. But Riemann was cocky. He went for the whole enchilada. He solved the general problem for n-dimensional planes. N is the variable used in mathematics for number of dimensions. So in Riemann's treatment, any space of any number of dimensions, 100 dimensions, 200 dimensions, can be studied by examining the rate of change of curvature of each one of its points. 70 years later, after Riemann, Einstein rediscovered this. He showed that Newton had thought of the universe as existing within an absolute space, a gigantic shoebox that was this coordinates. And he said, there's no shoebox. There's no absolute space. Space can be studied exclusively by looking at the local properties of a particular zone of it and seeing the rapidity and slowness with which curvature changes at that point. He showed, for instance, that the gravitational field of the sun would curve space around the sun. And that would show, if you took photographs of two stars whose positions are well known at night, took a photograph and measured the distance between the two, and then you took a photograph during the day when the two stars are behind the sun, the rays of light from those stars that are supposed to follow straight lines would be slightly curved by the gravitational field of the sun and would appear slightly displaced in a photographic plate. The only problem is you can't photograph the stars when it's doing the sunlight because the sun blocks them out. So in 1919, there was a solar eclipse. The French, the British, the Germans sent expeditions to several points of the planet to wait for that moment at which the moon was going to be in front of the sun. When those two stars were there, take photographs, measure the distance, and it was exactly what Einstein had predicted it would happen. Einstein in that moment became a superstar. But the real superstar was Riemann. The real superstar was Gauss. These guys invented the technology, the software to do that. Yes, it took genius for Einstein to see this represents the absolute space of Newton. Let's get rid of it. Let's move to local spaces. But the software, the most important thing, had already been thought by Riemann and Gauss. The final character here, and I don't want to extend this too much, is Poincaré. Perhaps the latest mathematician who was able to command a view of all the mathematical fields, to write essays in every single mathematical field. Today, mathematics is way too wild for anyone to pretend to do that. Poincaré writing at the end of the 18th century. He's co-inventor, by the way, of relativity theory. Relativity theory is normally ascribed to Einstein, but Poincaré was older than Einstein, had already thought many of those ideas. Many authors today credit both for the invention of that, but Poincaré went actually beyond that. Because Poincaré said, let's imagine, by the way, these n-dimensional curved surfaces are called manifolds or multiplicities. In French, I believe it's the same word, but in English there's two words, so you can get confused. Deleuze adopted the word multiplicity is like one of his most basic terms. In What is Philosophy? He begins the chapter, what are philosophical concepts, by saying concepts are multiplicities. In other words, he's saying, I trust mathematics more than linguistics to define what a philosophical concept is. But of course, it's not at all clear how we go from that to that. Let me explain. What Poincaré did was to say, why don't we give labels to each one of the dimensions of a manifold, of however many dimensions, this is a two-dimensional manifold, labels that represent physical quantities. For instance, this dimension here can be temperature, while this dimension here can be pressure. Systems for which these two variables are crucial are, for instance, a steam engine. Steam engine is a system that can be represented mathematically simply by changes of temperature and pressure. There's also volume, but I cannot draw a three-dimensional curved surface, so I'm going to leave it at that. I'm simplifying a little bit. So what Poincaré did, basically, was to link something that was completely abstract to something that was concrete. How to represent the dynamics of processes within these spaces. Once Poincaré called this phase space. Once the dimensions are given a particular meaning, each one of the points here, each one of these rapidities and slownesses, becomes a possible state for the system. Since the system is defined, I'm obviously talking about a very simple machine, a steam engine, at every one point in time, the steam engine is defined by a particular temperature, and by a particular pressure inside the pistons, and the temperature from the boiler. So a particular temperature and a particular pressure gives you a point here, and that point now is a possible state for the steam engine. And the complete full phase space is a collection of all the possible states that the steam engine can have. Poincaré took Riemann and married him into physics. And because Poincaré, and I'm going to explain how this, slightly more in a second, but Poincaré left very few disciples, most of whom spoke French. I mean, most of whom were French. The tradition of phase space also continued in the United States and Russia, but sporadically and not exactly with the focus that it had in France. In France, this was taken to a new level by a mathematician called René Thom. It's another one of our characters here, another one of our singularities. René Thom invented what is called catastrophe theory. Catastrophe theory is a version of Poincaré in more dimensions. So from Poincaré to René Thom, there's a series of people who left work that is not translated into English and therefore not available to English-speaking philosophers, but available to Gilles Deleuze in the 1960s.